Hello, everybody. To start with today, I'd like you to answer this question. Where is the smallest bone in the human body? Think about it. Is it like in your toes or your wrist? There's a lot of small bones in there. It's actually in your ear. And there's three of them that are very tiny, all inside the ear itself. We're going to learn today why those three bones exist and what they do. And we'll learn how our bodies are able to create sound and detect sound. We're doing this because, of course, we are connected in this electromagnetism unit, and we'll eventually be creating an audio speaker. And so it's important to know how sound is generated. Before we dive into sound directly, though, and the body and human ears, let's take a brief look back at yesterday's work looking at electric motors. This was a question that I asked you at the end of last night's work. Which way does the loop of wire rotate? The question is, does it go clockwise, counterclockwise, or does it not rotate at all? Well, in order to answer this question, we need to use one of our right-hand rules. In fact, the third right-hand rule is ready for this one overall. So let's look at some things that we already know. First, let's look at the direction of the magnetic field. Magnetic fields go from north to south, and so I'm going to draw them in with these red lines here, from north to south, so going to the right. Secondly, we need to know the direction of the current. Current is determined by the positive and negative, and I have the plus on one side and the negative on the other, so it will be up in the wire that's on the left and kind of down towards us in the wire that's on the right. So, what direction is the force on these two wires? Well, the third right-hand rule can help us to get there. In the third right-hand rule, the thumb stands for current in FBI. The index finger is your magnetic field, that's the red lines, and your middle finger is the force. So to line these things up, I would use the currents kind of into the page on the wire on the left and out of the page on the wire on the right. The magnetic field is always going to the right? And therefore, on the wire on the left, I feel that it has a force going downwards. Try it out. On the wire that's on the right, it will be the opposite, with a force going upwards. That means that this wire is going to be pulled down on the left and up on the right, thus turning it in a counterclockwise direction. Takes a little bit of practice, but the more you see this, the better off you'll be. All right, let's get into our discussion of the basics of sound and sound generation and detection in the human body. At the end of all this, I've got a quizzes on the human ear for you to try out. All right, let's start with your actual creation of sound deep within your body. The picture on the right is a picture of what we call your vocal folds. Previously, those were known as vocal cords, but they're not really cords at all. You can see that it's a couple pieces of skin that when your lungs are able to push air up through your trachea here, that it is able to go past these two vocal folds. And if you tighten up the muscles on the outside of them, it causes them to vibrate, just like you would imagine for like a trumpet or when we make a raspberry with our lips. Right? That vibration, therefore, causes what we think of as sound. 440 vibrations per second is known as the note A. And if I grab my ukulele for a moment, that is the highest string or the uppermost string on the ukulele here, which sounds like this when I sing it. Ah. So there are my vocal folds in my throat, ah, are vibrating 440 times per second. Those vibrations then come past up the larynx itself and the pharynx, which are these two pieces, eventually outside of the mouth that I might speak, or they might bounce around inside the nasal cavity, and all of the different space that's inside my head gives my voice my sound. When I have, my nose pinched, my voice sounds different than if I allow my voice to be open. And so the shape of the cavity in the head also affects the overall sound that I can make. Pretty amazing. Well, let's talk about what happens once that sound comes out of the body directly. Sound has to be made in some form of a medium. It has to pass through something. If I'm in outer space where there is little to no particles that are there, sound can't pass. If you're ever watching, a science fiction movie like Star Wars or otherwise, and you see a spaceship fly by and it screeches as it passes, if you are watching another spaceship in outer space, you would see it go past, for light can go through empty space, but sound can't. It just adds to the movie if we have the actual sound. So what kinds of things can sound pass through? Well, most commonly air. Air is all around us. Is what is actually currently getting the sound from me, passing through my computer, through my speakers, or your headphones to you. But in order to get it from wherever it might be through the air, we need to create what are called compression waves. Compression waves are sound movements, vibrations that go through the air. Now, if I look at this particular picture here, there's a compression that appears like it is moving to the right, if you can maybe spot that. On the other side of things, it looks like that there's kind of behind it something moving to the left. If you squint, for instance, at the page, it looks like you've got compressions going to the right and some sort of lower density kind of aspect going to the left. However, if you pay close attention to any one dot on the screen, you'll notice that it actually isn't moving from left to right or right to left. For instance, keep your eye on this red dot in the middle. You'll notice that it is only moving backwards and forwards. That's the nature of waves. Waves are vibrations that allow information to pass through, but don't actually move any matter other than small distances. And so these compressions made by my vocal cords and eventually coming out of my mouth in the air are what are passing through the air. What's amazing to me is that my small voice, my small vocal cords, can vibrate the air enough for people to hear me in great open spaces. If I went out in the middle of the football field and I yelled, you could hear me from all distances around the football field because my small vocal cords can push enough air that these vibrations, keep in mind, it's not a wind, right? These vibrations can go in all directions and reach anybody on the field. Pretty amazing. So, looking closely, sometimes the compressions are known as rarefactions. You can see them on the bottom. And each individual particle is just moving backwards and forwards. So, once we've now created the sound in our bodies, right, and our vocal folds have created the vibration and they've come out and they've now passed through the air in these compression waves, we have to get to the ear to be able to detect them. Your body has these interesting folds on the outside of it. This is called the outer ear, sometimes known as the pinna, P-I-N-N-A, and all of these different folds on the outside of the ear allow primarily for you to capture more sound, as you can, of course, put a cone on the outside of it or cup your hand to be able to hear more. But they also allow you to tell what direction the sound is coming from. All these different kind of little folds allow you to make decisions about, is the sound in front of me, behind me, my left, or my right? Eventually, though, enough of those vibrations in air are able to make it into the ear canal, this part here, the external acoustic meatus, making their way through. So we've got vibrating air that makes it inside the ear canal and eventually gets all the way up here to the eardrum, tympanic membrane. The eardrum is only about the size of maybe a half of a dime and can vibrate in and out, which then touches onto the three smallest bones in the human body, the malleus, the incus, and the stapes, or stapes, depending on who says it. All three of these bones amplify those vibrations that then push against the bottom of another organ inside your body that is the shape of a snail, a round, kind of rolled up snail. But the cochlea, this organ inside your body for hearing, is only about the size of a garden pea. It's not very large at all. Above it, you might see these three tubes. We've talked about these once before. These are the semicircular canals, which allow you to be able to detect if your head is right side up, upside down, or tipping from side to side. So they're with balance. And they connect in here to this kind of vestibular nerve, being able to balance yourself out, so getting signals, electrical signals to the brain. The cochlea, on the other hand, is what does most of your audio processing, and we're going to talk about that next, passing out through the cochlear nerve. There's also another tube that connects down here called the eustachian tube. That eustachian tube actually connects down into your throat, right, and connects to the inner ear. So your inner ear is not fully isolated from the atmosphere around us, which is why if you fly in an airplane or you dive down deep in water, your ear might start to hurt a bit because of changes in pressure on the outside of your ear. In order to help you kind of not be, in that pressure state so much, if you're diving down deep under the water, you can pinch your nose and blow a little bit into your body, which will then put air into the eustachian tube and equalize the pressure behind the middle ear and the outer ear, so that the membranes themselves don't have undue stress on them. You can also try and yawn or wriggle your jaw around to try and release air from inside of the eustachian tube to be able to regulate that if you were to fly up or go into high altitude. I'd like to show a nice short video here that's clean from the NIH, the National Institute of Health, that's about the journey of sound to the brain. They're going to get into a lot deeper inside the cochlea, so listen carefully. Here it comes.
Have you ever wondered how sounds make their way from the source all the way to your brain? Take a trumpet, for instance. When it's played, it makes sound waves in the air. The outer ear catches the waves, which then travel through a narrow passageway called the ear canal. The sound waves reach the eardrum, which is a membrane roughly half the size of a dime. They make the eardrum vibrate, which in turn vibrates three tiny bones called the malleus, incus, and stapes. These bones amplify or increase the sound vibrations and send them to the cochlea. The cochlea is shaped like a snail and is the size of a garden pea. It is filled with fluid, and the sound vibrations make this fluid ripple, which creates waves. Hair-like structures called stereocilia sit on top of hair cells and are grouped together as hair cell bundles inside the cochlea. The hair cells inside the cochlea ride these waves, and the hair bundles are moved. The hair bundle on top of the hair cell turns these movements into electrical signals. As the hair bundles are moved, ions rush into the top of the hair cells, causing the release of chemicals at the bottom of the hair cells. The chemicals bind to the auditory nerve cells and create an electrical signal, which travels along the auditory nerve to the brain. Different hair cells respond to different frequencies of sound. The hair cells at the base of the cochlea detect higher-pitched sounds, such as a piccolo or flute. The hair cells toward the top of the spiral detect progressively lower-pitched sounds, such as a trumpet or trombone. At the very top or apex of the spiral, the hair cells detect the lowest-pitched sounds, such as a tuba. The auditory nerve carries the electrical signal to the brain, which interprets the messages as sounds that we recognize and understand.
Nice and clean. All right, so there's the whole journey, right? From the outer ear, through the ear canal, to the tympanic membrane or eardrum, across the three bones, pushing through the cochlea, and through the auditory nerve in the end. The cochlea has lots of different structures. In fact, if you were to unroll it, you would see that it actually travels down and then around the edge and then back out again through the oval window. So there's a couple oval windows, there's an oval window here and then a round window there, which is where kind of the vibrations kind of meet. There's a basilar membrane in between, which separates the two things, and these little hair cells you can find throughout the length of the entire thing. as we go. In fact, the cochlea, even though it's the size of a garden pea, is about 9 millimeters if it were unrolled. That's not very big. 9 millimeters isn't even an entire centimeter. You can see the hair cells on the top of it. I don't know if you've ever had an experience before where your ears have rang or had that ringing sensation after maybe you've gone to a concert or been in a loud space. Sometimes it even sounds like the world is kind of dead, like you can't hear the sound around it. And then what's going on in that case is that those hair cells have vibrated back and forth, and they have kind of laid down or kind of been stuck down as things go. And which means they're not able to vibrate as much. And the hair cells kind of putting themselves back up is the way that you end up getting these errant sounds that are not truly in the environment around us, right? That pinging noise or ringing sound on top of it that you hear after a loud noise. Some people, like myself included, actually have a disease or a condition, maybe I should say, that ends up giving a ringing sound at all times. So I can't actually find silence in my own life. Whenever the environment gets really quiet, I notice that I have a ringing noise that's quite loud at all points. So that is a frustrating thing to find out, but it is important to recognize that we have all sorts of different ways of interacting with the world. And for me, I am always hearing a bit of a ringing noise, and the quieter it is, the more prominent I pay attention to that. So that's kind of interesting. All right, so we've got these hair cells, and they can get damaged, as I said. Sometimes that damage is from loud sounds. For those of you who wear earbuds or earphones quite a lot, I was talking to an audiologist once, and she said the most important thing you can tell your high school students, out of everything, from my perspective, is to turn the volume down on your headphones, because you can damage your hearing forever if you're not careful. Those hair cells can actually get vibrated so much that they get ripped apart, and so that they will never return. And hearing is such an important part of our world, especially for those of us who love music. So we've gone through a bit of understanding for the human ear. It's time for you to go ahead and turn your attention to see if you can figure out how to answer the questions in a quizzes. So thanks for listening, and